This video described the design, the production, and the testing of these new 3D printed vacuum chucks for the lathe. This video is a follow-up video to my previous video on the production of these wood segmented eggs. In order to finish the second surface of these eggs, I needed to mount these in a vacuum chuck on my lathe that I could both contour and sand the finished surface. So as a result, I designed a series of vacuum chucks, all different sizes to fit the different sized eggs that I normally produce on my lathe. The vacuum chuck is actually consists of two components. It consists of a base, which is printed out using PLA plastic, and then a vacuum sealer gasket, which is printed out using TPE plastic. I use TPE for the gasket because it's a softer material and has a consistency much like silicone abuna to make a good vacuum seal. This video describes in some detail the design of the vacuum chucks using the Fusion 360 software, and also I'll be describing the parameters used to print these out using my Bambu 3D printer. As I stated earlier, these vacuum chucks consist of two components, the main body and the vacuum sealer gasket. I first designed the main body of the vacuum chuck. This drawing describes the dimensions for a 3.5 inch diameter vacuum chuck. The base of the vacuum chuck was designed using the same dimensions that were used for the 3D printed faceplates described in the previous video. It was designed for a 1¼ inch diameter by 8 threads per inch size from a Powermatic lathe. For the design of the upper flange portion of the vacuum chuck, I used the parameters functions in the Fusion 360 software. The parameters function enables me to quickly and easily change the dimensions of the upper flange area of the vacuum chuck to produce a whole series of vacuum chucks from 2¼ inches in diameter up to 5 inches in diameter. In the Fusion 360 software, I first designed the base or hub of the vacuum chuck. This base is 2 inches in diameter by 1.5 inches tall. It contains a small counter bore as well as a 1¼ inch by 8 threads per inch threads. I next drew in the cross section of the upper portion or flange area of the vacuum chuck. Notice that the radius of the flange is labeled as FX 1.75 inches. This FX designation signifies that this dimension is retrieved from the parameters function in the Fusion 360 software. The thickness of the flange is 0.25 inches thick to provide for the required strength of the vacuum flange. This cross-section area is then rotated around the base hub to produce the basic shape of the vacuum flange. I next added some fillets to smooth out the overall shape of the vacuum chuck and also to round over the top edge. I then rotated the position of the vacuum chuck to better visualize its shape. From the top Modify tab, I select the Parameters function. Notice that the function V-diameter is listed as 3.5 inches, which is the initial design diameter for this vacuum chuck. If I change its value to 5.0 inches and click OK, then immediately I have a new vacuum chuck design that is 5 inches in diameter. This parameter function enabled me to create a whole series of vacuum chucks from 2¼ inches in diameter up to 5 inches in diameter in a matter of seconds. Next, I need to design the vacuum seal or the vacuum gasket for this vacuum chuck. This drawing lists the basic dimensions of this vacuum gasket. Notice that I'm again using the same V-diameter parameter to dimension the vacuum gasket. I just used some basic math functions to calculate the various dimensions for this gasket. For example, the overall diameter of the vacuum gasket is listed as 3.75 inches, which is calculated by adding 0.25 inches to the V-diameter function. This provides for the overall thickness of the vacuum gasket. Also, for the inner diameters of the vacuum gasket, I reduced the size by 0.005 of an inch. This will produce a gasket that will tightly seal against the main body of the vacuum flange. In the Fusion 360 program, I drew the vacuum gasket on the same drawing as the main body for the vacuum flange because I'm using the same V-diameter parameter to dimension both the main body as well as the vacuum gasket. For each of the gasket dimensions, I just entered a calculation to set the dimension to the required size. From this drawing, the gasket overall shape was achieved by extruding the various parameters. First by extruding the bottom or base to 0.40 inches thick, and then extruding the two edges or sides by 0.75 inches. Finally, I added some fillets around the edges. The top surface was rounded to a radius of 0.25 inches. Again, this demonstrates the power of the parameters function in the Fusion 360 software. By just changing the one V-diameter dimension in the parameters tab, I can produce a new design or dimension of both the main body and the vacuum gasket at the same time in a matter of seconds. The main body for the vacuum chuck was printed out using PLA Plus filament material. In order to get a good finish on the threads, I used the same parameters that I used for the face plates described in a previous video. On the Quality tab, I set the layer height to 0.12 millimeter and the ironing of the topmost surface to a line spacing of 0.05 millimeter. On the Strength tab, I set the wall loops to 15 and the sparse fill density to 90%. Printing out of the vacuum flange bodies required 5 to 10 hours depending on the size of the vacuum flange. For the vacuum flange gaskets, I used TPE filament material. This was the first time I'd used this filament material, and at first it was a little bit challenging. I needed this filament material because it has a rubber-like elasticity. It has a shore hardness of 75A and is recommended for gaskets. Therefore, it should make a good seal on the vacuum flanges. I would compare it to materials such as silicone or Buna-N, which are used for O-ring seals. The basic perimeter parameters had to be changed. The base plate on the 3D printer is not heated, and the nozzle temperature was increased to 235 degrees C. I'd lower the printing speed down to 30 millimeters per second. I printed these gaskets out on my new Bambu A1 printer, which does not have a heated chamber. When I brought in the drawing from Fusion 360, I did need to turn that part upside down due to the 1/4 inch radius on the top surface. It was recommended that I use some support material, but I was able to print the gaskets out without using any support material. I felt that it would be important to get a smoother surface on the gaskets in order to get a good vacuum seal. Therefore, I did make a few changes in the software setup. On the Quality tab, I set the layer height to 0.2 millimeter. And then I set the ironing to 0.15 on the top surfaces. On the Strength tab, I set the wall loops to 15, but I left the sparse infill density at 15%. On the Speed tab, I lowered the speeds to 30 millimeters per second, but I actually got better results when this was lowered to 20, but this took twice as long to print out. After slicing the program, it took over 10 hours to print out this gasket. The larger gaskets took even longer to print out. I produced a total of 10 different sized vacuum flanges to enable me to turn a variety of different segmented egg sizes. The smallest vacuum flange was 2.25 inches in diameter. Then I increased the sizes by 1/4 inch for each of the additional vacuum flanges, with the largest vacuum flange being 5.0 inches in diameter. I prefer to have as much surface area in the bottom of the segmented egg exposed to the vacuum as possible in order to get the optimum vacuum pressure on the segmented egg surface. With the small 2.25 inch diameter vacuum flanges, I only have around 50 pounds of vacuum pressure. While this may be enough pressure to sand the bottom of the eggs, it's not sufficient pressure to turn these eggs using a lathe chisel. In comparison, the 5.0 inch diameter vacuum flange will produce over 250 pounds of vacuum pressure on a larger segmented egg. This will permit the light turning of the egg bottoms. However, in all cases, it's important to remember that the vacuum chucks do not hold the material nearly as strongly as a faceplate or a lathe chuck, so all turning and sanding needs to be done slowly with only very light pressure passes with a lathe chisel. Well, here are the basic two components of the system, the base PLA system and then the TPE vacuum seal. And you see this has a cavity inside, and this is designed to slide right over like this and then seal it in place. Now so far I've been using this with no sealant of any kind in here. I could put vacuum grease in there, or I could put something like epoxy or CPA glue, and glue it in place. That would probably help, but I really found I didn't need it so far, so I'm not putting anything in it now, so I can always take it off and replace it. Needs to be replaced. I did do a little bit of light sanding on the seam here, because you see there's a seam. So I did a little light sanding on the surface here to get that smooth so it's kind of level. But I'm getting good vacuum seal on these. But again, there's two pieces to the system. The base system with the 8 TPI threads, 1.25 threads. And then the top piece, and this is a 1/4 inch radius curvature on the outer rim. And I did put a slight curvature on the base here just so that it's smooth. But again, it's just a friction fit. I say when I design these, this diameter is 5/1000 of an inch smaller on both sides than the diameter here and here. So it's a real tight fit. But that's the way the system goes together, and that's the complete assembled vacuum chuck. As the plastic threads, you gotta be a little bit careful with these threads because the threads they're not metal, they're plastic threads, so you have to watch you don't strip the threads. But it goes on the lathe quite easily. And on the lathe I have a gasket. This is the gasket, because you don't seal on the threads. You seal on this gasket to that surface. So it's just sealing to the lathe and this surface. So this goes on first. Goes in there like this, then this screws on. And just finger tight's all it's required. And I like to get as much surface area as I can on the pieces. Because if I was trying to put this big piece on here, there's not a lot of surface area on here. So by getting a smaller piece for this size chuck, this has almost a maximum coverage. So when I turn my vacuum system on, I had to turn the volume down on the video because the noise of the vacuum pump was overriding my voice on the system. But I had this thing turned on. I turned the vacuum pump on, and I got down to about 26 inches of mercury, going down to 27. Have a nice tight fit. If it's off a little bit, you can pound a little bit and twist it to make sure it's perfectly straight. But it's in there pretty good. And then I can turn the lathe on to show you how it turns. And see, it's off a little bit, so I can turn it off. And then I can see where it's out of alignment a little bit. I can pound it a little bit, turn it back on, and that's near perfect now. So that's being held with almost 27 inches of mercury now. This is my vacuum system setup. It consists of a small vacuum pump with a filter and then a larger expansion chamber. This expansion chamber was constructed from 4-inch diameter Schedule 40 PVC pipe. The PVC pipe has a wall thickness of about 1/4 inch, so it's plenty strong to hold the vacuum. This expansion volume chamber helps maintain the pressure of the entire system should you develop a small leak, experience a minor change in pressure, or when you open the valve to the lathe spindle. There are 2 vacuum gauges on the system. One gauge is for the vacuum pressure in the expansion volume tank, and the second gauge is for the vacuum going to the lathe. There's a 1/4 inch turn on-off valve between the 2 gauges. The vacuum hose then connects the vacuum system to the rotary vacuum chuck adapter. This rotary vacuum chuck adapter slides directly into the headstock spindle on the lathe with a series of O-rings to provide an airtight seal that enables the lathe to turn freely while maintaining the vacuum pressure inside the spindle. This part of the video is being shown at 5 times the actual speed for viewing purposes. Here's the actual vacuum system in process. First I turn on the power switch to turn the power on to the vacuum pump. You see in the gauge on the left the pressure drops quite rapidly down to about 27 inches of mercury. After it reaches full pressure, I then open the valve to open the vacuum to the lathe. You see the pressure is at 25 going down to 26 and eventually goes down to 27 inches of mercury. And here's the actual vacuum chuck holding a egg. Then I turn the lathe on to show it maintains pressure throughout the system. And I continue to maintain pressure down to 27 inches of mercury with no change in pressure. The following are the videos of the finishing of the bottoms of several segmented eggs. These videos are all being shown at 5 times the actual turning speeds in order to reduce your viewing time. After the first side of the segment egg has been turned and sanded smooth, I unscrew the egg and faceplate from the lathe headstock and screw it into the rotating adapter on the lathe tailstock. I next screw one of my vacuum chucks with a sealing washer into the lathe headstock on the lathe. The segmented egg on the tailstock is pushed tightly against the vacuum chuck and the vacuum is turned on to firmly hold the egg in place. Alignment of the segmented egg while still on the faceplate assures a perfect alignment of the segmented egg on the vacuum chuck on the lathe headstock. I then use my pointed carbide tool to do a final shaping of the base of the egg, and then use a parting tool to cut the egg loose from the wood plate on the faceplate. After pulling the tailstock away from the segmented egg, I finish turning the contour of the bottom of the egg using a carbide turning tool. I next sand the surface of the egg starting with 180 grit sandpaper and then progressively sand with finer sandpapers, ending up with an 800 grit sandpaper. The vacuum is turned off, and then as soon as the pressure is released, I remove the egg from the vacuum chuck, and this is my finished segmented egg. This second example follows the same procedures as the first example. The segmented egg on the headstock was removed and transferred to the rotating tailstock. The vacuum chuck attached once again, and then the vacuum turned on and the base of the egg contoured once again, same as done previously. It was then cut off using a parting tool. A final shaping at the bottom of the egg was done with a carbide cutting tool, and then the egg bottom was sanded using sandpaper, was done previously. After the vacuum was turned off, the segmented egg was removed from the vacuum chuck, and this is the finished segmented egg. This was a special design segmented egg that I made with a ring around the center, but the process is pretty much the same. Again, attaching the segmented egg to the tailstock, installing the vacuum chuck, and then finishing the shape of the egg by contouring the bottom of the egg with a carbide cutting tool. However, I did not use a carbide cutting tool to finish the bottom after removing it from the tailstock. I just used sandpaper to finish the surface and sand everything smooth. And then once again, after turning off the vacuum system, I removed the finished egg from the vacuum chuck. One of the advantages of having a 3D printer in your shop is the ability to create custom jigs for your shop, such as this new flat plate vacuum chuck that I just designed and printed out today, actually in the middle of editing this video. Instead of having a rounded surface on the top edge of the vacuum chuck, this new vacuum chuck has a flat plate top surface. This vacuum chuck is designed for holding projects such as this segmented bell or the bottoms of small bowls. I made two different styles for the gaskets or seals on these flat plate vacuum chucks. The first idea is to use a 3D printed gasket with a rim, much like the previously described gaskets. The gasket has a flat top surface and it fits onto the vacuum chuck body and is firmly held in place. The other option is to use these neoprene foam rubber sheets with an adhesive backing. This actually might be a lot cheaper and faster than the printed gaskets, because a 3D printed gasket took over 9 hours to print out. This adhesive back gasket material is very inexpensive and seals quite nicely on the surface of the flat plate. This material seals fine on this flat plate surface. I had tried to use this material on these other vacuum gaskets. Initially it sealed around the top and side surfaces, but eventually the edges came loose around the curved surfaces. So I'll now put both of these new flat plate vacuum chucks on the lathe and test them out. After I installed a flat plate vacuum chuck with a neoprene gasket back seal onto my lathe, I attached my segmented bell to the gasket seal and turned on the vacuum system. The bell was firmly held on the vacuum chuck with a pressure range of around 25 inches of mercury. I turned on the lathe to verify that the vacuum system was working properly with the lathe turning. Then I turned off the vacuum, removed the bell, and tested the smaller bowl. Again, the vacuum chuck worked perfectly and held the bowl firmly in place. I repeated the process for the other flat plate vacuum chuck with a 3D printed gasket. This flat plate vacuum chuck held the egg and the bowl firmly in place with a vacuum reading of around 25 inches of mercury. This concludes this video on the design, the production, and testing of these 10 3D printed vacuum chucks for my lathe. This video was produced to provide some guidelines for others to use their 3D printers to design their own lathe vacuum chucks. The vacuum chucks designed in this video did require the use of two different filament materials on the 3D printers. The TPE filament was a little bit of a challenge since it was the first time that I used this material, but I was able to produce the two-piece vacuum chucks that worked perfectly for the turning of the second side of the 19 segmented eggs that were described in a previous video. I've only had my 3D printers in my shop for less than a year, but they have proven to be an invaluable asset for design of custom jigs for my woodworking projects, storage holders for many tools, storage boxes for screws and other shop essentials, and several other accessories for both my wood and my metal shop areas. And my designs will continue. Here is a brand new prototype of a flat plate vacuum chuck that I just designed today. I designed this flat plate vacuum chuck to turn the bottoms of bowls and also the tops of some segmented bells that I plan on producing for Christmas this year. Once again, thank you for watching this video. As always, if you have any questions or concerns or comments, please give us a call or drop us an email. And once again, thank you for watching this video.